Welcome and good morning to everyone. Okay, we have lab 8 today, and it's going to be again a simulation like last time. It's going to be pretty easy like last time. Uh, and I think after this, we only have one lab to stream. I think, yeah, next lab 9, is going to be streamed from the lab live. That is going to be electromagnetic induction. So there are like 2 or 3 experiments that I will do. And I think after that, the last 3 labs that we have, 10, 11, and 12, will be all simulations as well. So the next lab will be streamed live. And if you haven't completed any past experiment that you need to do, and you might need some lab equipment to do that, next week, this time, you could be in the lab and get help. Use the equipment that we have. Um, there was an issue with the light bulbs. I haven't been able to find the light bulb. So if it has something to do with light bulbs, you might want to bring your own. But otherwise, we pretty much have everything. So yeah, please come to the lab next week this time if you have any pending labs that you want to do. Uh, are there any questions about the last lab that we had, lab 7? I think not, but does anyone have any questions? All right, yeah, was pretty easy. You know, you could do that in 5 minutes and then start writing your report. Today's lab is going to be like that. It's like, again, barely 5 minutes, and then you can start writing your report. It doesn't need to be extensive, doesn't need to be 6 or 7 pages report. You just write the little bit of theory that was used. You write the procedure. Well, the procedure is literally use a simulation. So you use a simulation, and this was the, for example, for the last lab, you could just write, this was my volume of water, and this was my voltage, and this was my current. This is what I chose, and then you fill in the table, answer the questions, uh, think about what you concluded from that and that stuff. So you could easily finish that in uh, 2 to 2.5 pages like that. If you do that, it's fine. It doesn't need to be 5, 6 pages. Um, yeah, and this lab is similar. And I've graded some labs, I think, until lab 4, so you could check that. I've left some comments where I thought they were needed. Some of you have missed parts of labs, so I've said that you have missed this. If you have missed entire sections of labs for some reason, you might do them again. Uh, some of you, most of you I think, did well on lab 3 and 4, so there was no problem. I think most of you are making good lab reports. Lab 5 and 6 are really the ones which take more time to grade, so that is in the process. But everything until lab 4 is graded as of now. And yeah, lab 7, 8, after that, it will be very quick. Okay, we can, yeah, we have enough people here. We have 10 people. We can start discussing this lab. And this is, again, going to be a quick meeting. I'm not gonna hold you here. So lab 8, this document is on Blackboard. Today we have the RC circuit. So you might have done these kind of circuits where you have a resistor and a capacitor in the same circuit. You might also have an inductor in there, so that becomes the RLC circuit. In this case, we just have a resistor and a capacitor, and we have discussed resistors and capacitors individually in previous labs before. So this is just them both in the same circuit. So what we are doing is, obviously, we know that when we charge capacitors, what do capacitors do? They hold up charge, right? They accumulate charge, and the theory goes like this: that when you have a parallel plate capacitor, and we know that one plate is going to be accumulating positive charge, the other is accumulating negative charge. So, for example, there's All right, when you have no charge on the plate, the positive charge starts accumulating. And as more charge is trying to accumulate, what happens is that charge that is already there is kind of repelling that, because it's a it's the same charge. It's positive charge or negative charge that is accumulating there. So as we know that similar charges repel, so you kind of have to do more work to move additional charge there. So that is the theory. So as you go on, you have to do more work to put charge on those plates or to charge that capacitor. So that is the theory. And the charge on the plates at any given time is given by this equation here. And Q is charge at any given time. Q naught is a maximum charge on the plates, as it says. And here in the bracket, we have 1 minus exponential raised to minus t over tau. So that is tau, and tau is just resistance into capacitance. So that is what tau is here. T is, obviously time. Right. And from here, we get something called a half-life. Now, half-life, again, you might have done this before in chemistry or in physics. It means something else. But just in this case, what it means is the time taken to charge the capacitor to 50%. So at 50%, the time it takes to get to 50% is called a half-life. And from here, you can get this equation for that half-life. So T half is half-life, and that is equal to RC or tau into natural log of 2. Natural log means base E, and you might already have this in your calculators, but simply, I think it's given here that, yeah, it's 0.693, so you don't even have to calculate that. So natural log of 2 is given. And in this activity, what you're doing is you're finding the charge in the capacitor, and you will be just verifying that. So you have this link, right? And I will show you what you will see when you open this link. By the way, I just want to make sure that everyone can hear me. Okay. Yeah, that would have been awkward if I was just moving my lips for 10 minutes. Right, because I didn't hear any sound at all. I just wondered if my headphones were working. Okay, right. Let's open the link, and it's where here. All right. So this is what you will see when you open this link, and it's again very simple. So you choose the resistance, as you can see, move the slider along, and choose some capacitance again, and then you get a plot between voltage and time. And in this experiment, we're using voltage as, I know we are measuring really charge, but it's not. We are kind of using voltage because we know uh, voltage and current, they are related. So we're kind of using voltage to measure that charge. So we are looking when voltage reaches 50%. So you do that, and this is some random values. And as you can see, voltage reaches 50% at this point, and you're gonna have to kind of guesstimate it. It's like what 1 point, what is this, 1.8, 1.7, 1.75. So it's kind of a guesstimate here. So this is the time it took to get to 50%. So this is the t half that you get from the plot. And if you go back, you can see that they have given you values. So R should be this and C should be this. So you put these values there, hit play, and you can pause anytime you want. You look at the plot and you find the t half. You write it here, and then you actually calculate the t half, because so you get some t half, right? And you then find C. You have chosen some C. You just want to verify if it actually works, if this equation that we have really works or not. So you will get some experimental capacitance, and you will compare with the known capacitor that you chose. So capacitance here was 1.3 farad. Then it's not really experimental, but it's come from the simulation. So that's what you will write here. C is equal to T half, which you get from the simulation. R that you are choosing, again, in this case is 1.2 ohms. And use this equation, you'll get some experimental capacitance. You compare it to the known capacitance, and then you find the percentage difference. And again, experimental minus theoretical over theoretical into 100. That is what we use. And again, pretty simple. You can do this in a minute. Again, same thing, choosing different values for R and C, and you will again find the half-life, and you're gonna again do go over the same process really, and experimental capacitance, whatever, and then you find a percentage difference. In this case, the theoretical capacitance is 2.1. Yeah, that's pretty much it. And in the end, you got 3 questions based on the simulation. Again, they are very, very simple. And this is all you have to do. And this is all you have to do for this lab. That's it. I just saw someone actually just entered the meeting, and unfortunately, we pretty much ended here. Do you actually? I don't think I've uploaded the last meeting that we had, because I thought, it was like we met for what, 15 minutes, and I didn't think it was important. You want me to put that meeting on YouTube as well, and maybe this one too? If I can do that, if you guys want that. Okay. All right. So maybe I'll upload to YouTube. So these are simple, really. If you just look at the documents, read it, and follow the instructions, you will know everything. And they're not that hard. But anyway, I'll still put the videos up on YouTube so that you can watch them if there are any questions. And then again, if you have questions, you can email me. But that's really it for Lab 8. It's again pretty simple. Lab 9 will be a bit more. There'll be a bit more theory going with induction. So we'll talk about that first, and then I will do the experiments next week. Again, you're welcome to be in the lab if you want to do any experiments. After that, it's just some simulations. So yeah, that will be it for this lab. If you guys don't have any questions, you are free to leave. I'll see you next week.